Thank you very much for inviting me. I've been following the seminars throughout my PhD, and I think I just hope I can convey something interesting to everybody now as well. I finished my PhD already last summer, so for me it's a long time ago, and I just hope I can still explain everything well enough for you. Friedemann Samrock and Alexander Greiver have been supervising me closely, and they also do not work with this project anymore, not at ETH anymore, but they are still in MT. So my entire PhD project was the magnetotelluric investigation of active rifting and the formation of geothermal energy resources in Ethiopia. And we were really interested in this project because, as Kate has explained, we have this East African rift system. And because of that, of course, we have a lot of magmatic activity and heat flow. So this makes up for a perfect environment for geothermal resources. And in a country in Ethiopia, where I think 2017, still 45% didn't have access to electricity, this is, of course, a thing one would need to look into. So our aim was with magnetotellurics, because it is super apt to image conductive magma and conductive geothermal systems, to image these systems from the deep magmatic roots and thus the heat source to the surface. And while doing so, we also hope that we can contribute to the general understanding of rifting and volcanic hazards as it has been depicted so far. So in the bottom here, you see an image that actually school kids in Ethiopia draw, and I think it depicts quite well the understanding that the asthenosphere beneath the rift valley is upwelling, and then we have decompression melting, and then a melt ponding zone in the lower crust, and then this migrates upwards to the volcanoes. And while many studies have been made on that, none has shown this in such a nice pictures as the school kids have drawn it. So we hope to maybe with MT contribute to that. So the first study I present is on Corbeti volcano. In the image, you see the caldera here, and it has been published last year in JGI. And about Corbeti, what was interesting is, on the one hand, so it's located here, just on the verge between the central main Ethiopian Rift Valley and the southern one. And the interesting thing was, on the one hand, that production drilling was about to take place. And the other thing is that Corbeti has been uplifting for a long time at a steady rate, which is not happening at all the volcanoes in Ethiopia at all. And Gottsman et al. Interpreted this to be an active magmatic intrusion. So what we wanted to do now is really image this intrusion, and we were so lucky to get data from Reykjavik Geothermal. They were so nice to share them with us. And of course, they interpreted them before, but now we wanted to perform really a new 3D inversion to see this magmatic and hydrothermal system together. And for that, we used the numerical GoFam code that Alexander Greiver developed that uses non-conforming, unstructured, and hexahedral meshes and can integrate the topography correctly. And for the Corbeti dataset, so you see the mesh here, and the station spacing was quite close, so we decided to go for phase tensor inversion, so for the MT people. Just as a background information, and we got a nice fit over all stations and at all frequencies, so we can really interpret this model in 3D. And I show you now a video of a profile slice going from the south to the north. And you can see that we have a conductivity anomaly in the lower crust, and then a channel piercing up just in the caldera, and then the crust gets resistive again. So taking into account the previous studies, we really interpret these conductors C1 and C2 to be caused by conductive magmatic melt. And as I said, the study from Gottsman, based on microgravity, they predicted a magmatic intrusion, and they predicted it to be at about 7 kilometers depth. And if we plotted in our model, the purple ball that you see here, it fits quite well with the upper part of the magmatic marsh channel that we imaged. Also, the seismic hypocenters that I plotted here from Lavoisier in white, they really surround the channel and do not lie within it. So it would make sense that this is a ductile region. What we also noticed is, as I told you, Corbetti is really on this verge between the southern and central main Ethiopian rift. And it is believed that we have like transversal faults in that area, one really cross-cutting through the middle of the caldera and another one a bit south of it. So having that in mind, we thought it's interesting that the magmatic ascent channel really has a bit of complex shape and is direction here. But of course, to really relate this to the tectonic environment, we would need more information. But I thought in this seminar it's interesting to mention this observation we made. So the next thing we did is really to interpret the magmatic marsh system. We assumed that we have in the lower crust basalt that then migrates through the marsh and fractionates to rhyolite, as many geochemical studies have postulated for the Ethiopian rift. And we took the bulk conductivity that we modeled here in the lower part, and then we took a basaltic melt model from NI that depends on pressure, temperature, and water content. So we had the conductivity of the melt and the conductivity we observed. And then using modified Archie's law, we could estimate 6 to 16% of basaltic melt in the lower crust here. We did it very similar then for the upper part as well. And we estimated there 20 to 35% of rhyolitic melt to be present. So just to put it a bit into context, this is really melt fractions that are considered to be non-eruptible. So just that's good to know. So next thing, as we have imaged now, basically the heat source and the magma beneath the caldera, we can have a look at the geothermal system. And as you might all know, the hydrothermal alteration forms clay minerals that are very, very conductive and which topography basically delineates temperature isolines. And if we look at the system from Corbetti, we see that we have very thick clay cap outside of the caldera, and then a clay cap just north of this east-western fault structure that is thinner. And our interpretation then was that we have a paleo clay cap outside of the caldera and a new clay cap inside just north of this east-west fault system, and that we have an inflow from the south and then upflow of geothermal fluids in these areas, and where the geothermal gradient is maximum, we would have the thinnest clay cap here. So I think this is a good example, continuing the work that Friedman already did at Tulumoye before, of a geothermal system imaged together with its heat source. But in the beginning, I also promised that we also have a look at the rift in a bigger sense. And we did that at Aluto, where a geothermal power plant is already installed. And we published that in 23 in Solid Earth. And the idea was now really at Aluto, which is here, just a bit north of Corbetti, to get this image that the school kids drew. So the zone of melt ponding that originates from decompression melting in the mantle, and then having this whole transcrustal magmatic system up to the geothermal system. And to be able to do so, we combined two data sets, one that is very closely spaced at Aluto volcano, and a second one that crosses the rift. And we obtained these data from the Rift Wall project and from the Geological Survey of Ethiopia, and we're very thankful that we could do so to enable really imaging the structure underneath Aluto in detail and then have a wide aperture to look deep. And we perform modeling again with the GoFam code, and we put quite some time into the mesh. So we did a lot of receiver refinements so we can really have this multi-scale image that allows for this interpretation. And we decided to do first a phase tensor inversion and then a subsequent impedance tensor inversion, just to be sure that we still can constrain absolute conductivities and the parts where stations are a bit broader spaced in the profile arms, so to say. And both converged nicely, and you see the map of the RMS distribution here, which shows that most all stations are well fitted, so we can really interpret in 3D. So I show now video again of the model. It will be a slice that is moving in this direction.
Luise, you've used 10 minutes now.
Okay, thanks. And you see the MOHO here from seismic tomography, and you see that just above the MOHO, we have a conductivity anomaly in the western part that forms a channel going up right underneath Aluto. And you see the model again here on the left side, and we interpreted it similar to what we did at Corbetti. So we estimated again melt fractions to be in the lower crust to be 7%, and then the upper crust to be 10 to 15% of rhyolitic magma. And I think what we see here quite nicely on the first glance is that we could manage to image these broader regional structures in depth and across the rift, and then still maintain enough detail just beneath Aluto to also interpret that for the geothermal system. And Friedemann Samrock did that in his paper in 23 in geophysics, if you want to have a look. I think from a perspective from the rift structures, what is interesting is it has been long proposed from seismics that we have an asymmetric rift structure where we have the asthenospheric upwelling in the western part, in that part of the rift, and we just see that now as well and constrain it now as well with another geophysical method, MT. It is also, and this coincides, like we have the shallower MOHO here and we have the melt in that part as well. And then we have melt moving up, and not straight up, but towards the 1G fault belt, so this eastern fault zone. And these channels are also aligned with the major fault planes in that area. And this also confirms what has been predicted before, is that we have higher seismic activity in that area, as you see here, and thus we can probably assume that we also have dominant extension here. And it was also from geochemistry predicted that melt rises quite fast up beneath the 1G fault belt, while it doesn't do that in the more western Silti-Debre fault zone that is located here. And this seems to confirm that, because we don't see melt fractions here. So either in the western part, melt is ephemeral, or it's just a lot less than our stations were not closely enough to space to see it. But it's definitely not as well pronounced as in the eastern part. We also did sensitivity testing on that. So another thing that we also see is that both fault zones are fed from the same lower crustal magmatic ponding system, which is interesting to know because this has been discussed in the past as well. As you can see here, this is still depicted as two separate zones. I think to conclude, we drew these conceptual models from the Aluto region, from the cross-rift study, and from Corbetti volcano. And I think what we were able to deliver is really surface to depth multiscale models that depict these long hypothesized rift structures now nicely, and that show how strong MT is in resolving these structures and understanding the melt distribution along the rift and these variations on a larger and on a smaller scale. Yes, and at the end of the project, we and understand that in its whole tectonomagmatic context. At the end of the project, we ask an artist to draw this picture, which looks a bit dramatic, but I think it's nice because it shows really how important it is to see things, to spark further interest in such projects. And thanks to Friedemann and Alexander, and of course the Geological Survey of Ethiopia and everybody who supported the project.
That is awesome. Thank you very much, Luise. I have a quick question and I'll open it up. So I noticed you interpreted melts primarily as the source of this of the conductive anomalies. Could we also have contributions from volatiles or not? What do you think?
Well, I think for supercritical fluids, the electrical conductivities are still not so well understood. That is one thing. Of course, I mean, with these conductors, I think we cannot, it can be a bit deeper, and on the top there might be some conductive part from fluids as well. I think we cannot draw like a straight line and say this is really, the melt is until this exact depth. But I think that what we've seen at Corbetti, where like this model from Gottsman, from microgravity, and our model fit very nicely. And when we see how seismic hypocenters really surround the channel, this speaks for that. These are really ductile areas with melt fractions inside.
I see, great. I think Derek has a question. Please, if anyone has a question, we still have in a couple of minutes for more questions. Please raise your hands. Go, Derek.
Just a quick question. Do you have any thoughts on why the shallowest magma body is sort of always at 5 kilometers beneath Aluto, Corbetti, and also Tulamoyo was quite similar, I think, for Friedemann's results? Why? What's controlling that depth?
I think maybe I haven't. There was a study where they performed numerical modeling, and they always let melt come in again, and then they have. Isn't it these studies from Moulonnet? And then they observe at what depth the magma really stalls. So it's a long time ago when I read it. But I think modeling of these, I think probably something of it makes rheologically and thermodynamically probably sense.
Okay, thanks.
Maybe that's
I think Kathy Wheeler has a question. Please go, Kathy.
Yes, thanks very much. That was really interesting. I was going to ask you about your estimation of melt fractions or melt percentages. You used modified Archie's law. Was there any particular reason why you chose that, and whether you investigated predictions of any other model type?
I mean, modified Archie's law is more exact than Archie's law, right? Because we can also so that is basically the reason. Or would there have been another alternative?
Well, I was talking about Hashim-Strickman, possibly more likely upper bound, but upper or lower bound as well.
I mean, we tested, of course, different like cementation exponents, as you see here. Mm-hmm. But then, for example, this is Corbetti now. We for a cementation exponent of then 1.5, but then 48% of melt, that doesn't really make sense anymore. So this is how we made this estimation then.
Yeah.
I mean, we tried out like different ranges.
Yeah. I mean, there's quite a lot of options in SIG melts or anything like that, but you can put lower bounds on it by, for instance, using Hashim-Strickman upper bound. But yeah, thank you.